Hi, this is Srinivasan, Assistant Professor, Department of ECE. In this presentation, we are going to discuss on binary parallel adder, carry lookahead adder, and BCD adder. So let's start with binary adder. A binary adder is a digital circuit that produces the arithmetic sum of two binary numbers. So it is constructed with full adders connected in cascade with the output carry from each full adder connected to the input carry of the next full adder in the chain. The AND bits of A and the addend bits of A are designated by the subscript numbers from right to left, with subscript 0 denoting the least significant bit. So A corresponds to A3, A2, A1 and A0, and B corresponds to B3, B2, B1 and B0. C0 is the input carry, and S0, S1, S2, S3 is the output sum. C1, C2, C3 is the intermediate carry that acts as the input for the next full adder, and C4 is the output carry. The carries are connected in a chain through the full adders. The input carry to the adder is C0 and it ripples through the full adders to the output carry C4. The S output generates the required sum bits. A n-bit adder requires n full adders with each input carry connected to the input carry of the next higher order full adder. To demonstrate with a specific example, consider two binary numbers, A is equal to 1011 and B is equal to 0011. Their sum S is equal to 1110 is formed with the 4 bits of adder as follows. So let us consider the AND 1011, addend 0011. So first we will perform the addition of 1 plus 1. So 1 plus 1, the sum is 0 and carry is 1. So and the carry is moved to the next higher order. So it is added with 1 plus 1 plus 1 and the sum is 1 and carry is 1. Again 1 is moved to the higher order input carry, and 1 0 0 it will produce sum 1 and carry 0. And this 0 is forwarded to the next higher order full adder. So 0 1 plus 0, it leads to sum is equal to 1 and carry is equal to 0. So by which we obtain the binary adder. And next we'll move on to carry look ahead adder. In binary adder, the signal must propagate through the gates before the correct output sum is available in the output terminals. The total propagation time is equal to the propagation delay of the typical gate and the times the number of gate levels in the circuit. The longest propagation delay time in an adder is the time it takes the carry to propagate throughout the full adders. We are providing the inputs A3 and B3 at the same time. However, input carry C3 does not settle to its final value until C2 is available from the previous stage. Similarly, C2 has to wait for C1 and so on down to C0. Thus, only after the carry propagates and ripples through all the stages with the last input S3 and carry C4 is obtained. The problem can be resolved by using a carry lookahead generator. So, getting into carry lookahead generator, we need to understand the full adders with a specific notations. So the signals Pi and Gi settle to their steady values after they propagate through their respective gates. These two signals are common to all of adders and depends only on the input AND and addend bits. And when you move on to the next part, Si is implemented using Pi XR Ci, and Ci plus 1 is nothing but the next carry obtained by using Pi Ci plus G into I. So if you define two new binary variables, what we call it as carry propagate and carry generate. So carry propagate is designated as Pi, that is equal to Ai XR Bi. Carry generate is equal to Ai Bi, by which we can obtain Si is equal to Pi XR Ci. The next carry or next level carry Ci1 plus is equal to Gi plus Pi Ci. So Gi is also called as carry generate and Pi is also called as carry propagate. So from this we can obtain C naught is nothing but the input carry. C1 is equal to G naught plus P naught C naught. C2 is equal to G1 plus P1 G naught plus P1 P naught C naught. C3 G2 plus P2 C2, which in turn is designated as G2 plus P2 G1 plus P2 P1 G naught plus P2 P1 P naught and C naught. These functions C0, C1, C2 and C3 can be implemented by using logic gates. We are providing the addend and augend bits A and B and carry input C0, and carry look ahead adder produces the intermediate carry value C1, C2, C3 at the same time. So it reduces the generation of S0, S1, S2, S3 and C4. So the carry look ahead adder includes 4 full adders and the carry look ahead adder so as to produce the sum S0, S1, S2, S3 and the carry C4 with less time. And next we move on to BCD adder. So we have 2 different classification. One is called binary. It starts from 00002 1111, or we can call it as 0 to F. When it comes to BCD number, it includes only numbers starting from 0 to 9. That is 0002 1001. So greater than 9 cannot be represented by using BCD. In such case, each digits have to be represented by 4-bit values. For example, if it is 10, right, 1 should be represented by 4 bits and 0 should be represented by 4 bits. In this circuit, we are going to design a BCD adder which can act as a binary adder as well as a BCD adder. So differentiate the binary number with the BCD number. A BCD number, right, by adding a 6, that is 0110, it converts the correct BCD representation of the binary value. So binary sum, so it starts from 0 to 19. If it is BCD term, only 0 to 9 will be there. From 10 onwards, it will be represented as BCD representation. Conventional binary value for decimal 10 is 0, 1, 0, 1, 0. But in BCD, as I said, 1 should be represented by 4 bits and 0 should be represented by 4 bits. So 1 represented by 4 bits, 0, 0, 0, 1. So zeros don't have any significance over here. So we have represented only 1. And 0 is represented by 4-bit value 0, 0, 0, 0. And this pattern follows from 10 to the decimal value 19. The logic circuit that detects the necessary correction can be derived from the entries in the table. It is obvious that the correction is needed when the binary sum as output carry k is equal to 1. So we have starting from 100 through 1111 that need a correction have a 1 in position Z8. So the block diagram of a BCD adder. If the binary number or the sum of the two numbers is less than 9, so it acts as a binary adder. If the sum of the two numbers is greater than 9, then a 6 will be added through this output carry to the second binary adder so as to produce the correct BCD representation of the result. So to distinguish from the binary, which are also a 1 in Z8, we further specify that either Z4 or Z2 must have 1. We are obtaining a function C is equal to K plus Z8 Z4 plus Z8 Z2. When it is equal to 1, then 0110 is added to the binary sum through the bottom 4-bit adder. The output carry generated from the bottom adder can be ignored since it supplies the information already available at the output carry terminal. So when you go back to the diagram, if the sum of two addend and argand is less than 9, okay, it will forward the data to the next 4-bit binary adder. The output will be produced for the binary adder, BCD adder. If the sum is greater than 6, 0110 is added and we obtain the correct BCD representation.